Well, hello, let's get started. Rust as high-level language. First of all, a couple of words about myself. While Rust is a system programming language, I actually came to Rust from languages like Java, Kotlin, and Python. I did some C++, but it wasn't like serious C++ work. And that's why I'm going to tell you about Rust as a high-level language. Specifically, at JetBrains, I was implementing the plugin for IntelliJ platform, which was written in Kotlin, plugins for Rust, of course. But now I've left JetBrains and work at Rust consultancy Federal Systems, where I continue to work on developer tooling for Rust, but this time in Rust. So, what Rust is about? In 2 words, it's a memory-safe systems programming language. That means that Rust does not have a garbage collector. All memory is managed by the compiler at compile time deterministically. However, Rust, unlike languages, other system languages like C++ and C, does not have typical problems like use after free or buffer overruns or memory unsafety or in general any undefined behavior. Program in Rust which compiles is guaranteed to be memory safe. And this is really, really a big deal if you are coming to Rust from low-level languages like C++. Because if we look at the statistics for memory vulnerabilities in major code bases, we will see that more than half of security vulnerabilities are caused by memory unsafety in the language, are caused by things like double freeze or index or buffer overruns. And it is really awesome if you can just get rid of more than half of these vulnerabilities by just changing the language. That's really cool. And by the way, this is the graph for some of Microsoft software, but similar graphs exist for Firefox, for Apple software. So it's, in general, a problem with current systems programming languages. But if you are coming from high-level languages, such as Java or C# or Go, you shouldn't really care about this as much, because in a high-level language, you have a runtime, and runtime is the thing which manages memory safety for you. A runtime is responsible for freeing the objects only when there are no outstanding references to these objects. A runtime is tasked with checking that all your array accesses are actually in bounds and raising a clean index out of bounds exception and not reading some random memory if it's not the case. So this is not a benefit of Rust if you are using Java. Nevertheless, I think there are a couple of things which Rust has and high-level language don't have. And I'd like to talk about this. Really, the core of my talk would be the Rust support for multi-threading, which I really think is state-of-the-art. However, let's start with some more boring reasons to use Rust. First of all, it's plainly a greatly designed language. It has a nice type system inspired by experience with functional programming. It doesn't have null. It has some types. It has clean error handling. And the reason why Rust type systems feels like a cohesive whole and not like plug in some existing holes is that Rust don't have to be compatible with some existing runtime which already has nulls. So it was able to design its type system from scratch and arrive at something which, at least in my opinion, is a really sweet spot between complexity and expressiveness and simplicity and ease of understanding. Another interesting high-level characteristic of Rust is that it places great emphasis on data and not on objects in object-oriented sense. This is again subjective, but this data-oriented design, at least in my opinion, leads to programs which might be easier to understand and reason about, because it's easier to understand how the data flows through your program, and by understanding the data flows, you can understand the program as a whole, but that's really hand-wavy. And finally, Rust is language for the industry. It's a really pragmatic language. And for this reason, the concept of libraries is a a first-class concept in the language. Like there are not only types and modules, but also crates, which are a unit of compilation, which are a unit of visibility, and together with this support from the language, there is a great support for libraries from the tooling. Cargo, the Rust package manager, also often is prized like one of the best package managers out there. So this together creates a really nice and thriving ecosystem, which is not as large as in more established languages, but in general is pretty high quality and pretty robust to use, because you, like by definition, can't get name conflicts between symbols in different libraries. You can freely mix libraries, the same library with two versions in your binary, and nothing bad happens. So like, that's all nice reasons to use Rust, but they're not specific to Rust. They could exist in other languages. Something which is more specific to Rust is performance. This is the language without garbage collector. And in general, the compiled code in Rust looks almost exactly like the compiled code in C++. And you get the same C++ level of performance, except that you don't get memory safety errors. That's really nice, but only if your domain actually requires big performance. Most of the time, the performance of a high-level language like Java is just good enough. So like, performance argument is not a strong one for many domains, in my opinion. However, there are a couple of things which come with this performance which are more generally applicable. For example, programs in Rust tend to be much more deterministic than programs in Java, because you don't have garbage collector, you don't have a JIT. So when you run code, it usually takes the same amount of time, modulo some OS level scheduling and CPU frequency scaling shenanigans. So like, it's just easier to benchmark. Because Rust has no runtime, you can use it in more contexts. Just recently, a person at the local Rust meetup at St. Petersburg approached me and started telling me a story about how they're using this new web framework in Rust to write a web server, and they were having some trouble with it. And my initial response was, hey, like if you're writing a web framework, if you're using a web framework, why don't you use something like Python? Because like, a web ecosystem in Python is much more mature, and probably your problem will be solved in that ecosystem. And the person replied to me that, well, it's all good, but I'm running my web server on a microcontroller, and like Python wouldn't fit there at all. So with Rust, you can take your usual typical high-level program, high-level application, and compile it to something like WebAssembly, and we have a talk about it later. Or you can compile it to a native library and expose a CFFI C ABI to this library and use it from other languages. So like, you can reach more places. And the third interesting aspect of this performance-oriented language is that the abstractions in the language are designed in such a way that using abstractions does not give you performance penalty. For example, in Rust, if you replace a for loop with some ifs and something like that with a chain of iterators with high-level constructs like map, filter, flat map, etc., you are guaranteed to get the same performance as if you have written this code by hand. Like, using closures does not force an allocation on you, and this is like really great, but really not what this talk is about. This talk is about concurrency. And this is something I badly want in Java every day, because I write, at least while I was at JetBrains, I was writing concurrent Java code every day, and it was really, really unpleasant. But first, let me make a slightly controversial statement that writing multi-threaded code is actually really, really easy. You need only 2 steps. You write some code, and then you spawn more than 1 threads, and that's it. Of course, the tricky bit is making sure that this multi-threaded code is actually correct, because it's rarely happens so that, like, by just spawning a thread, you turn your correct single-threaded program into correct multi-threaded program, because together with spawning threads, you have to add necessary synchronization. You need to add atomic variables or mutexes around shared data and make sure that like you don't mutate data structures from 2 threads concurrently. And this is generally hard. Like you can run your test suite for your parallel program, but it probably won't show any problems because these problems only manifest themselves under high contention where there are like lots of threads. So there is a high chance that you actually face this problem in production. And what Rust fixes here is that it makes writing multi-threaded code hard. Specifically, in Rust, if your program contains a data race, a problem like incrementing some counter from 2 threads without synchronization, your program just won't compile. So you will have to spend a lot more effort convincing Rust compiler that your program is actually thread safe. But then, if your program compiles, you are guaranteed thread safety. To be clear, the only thing Rust protects you from are data races. Rust doesn't protect you from other concurrency problems like deadlocks or starvation. Nevertheless, data races are a majority fraction of all the concurrency problems. So the liberation from not having to worry about data races in programming is pretty great. I'd like to explain how this actually works. And to do this, I need to touch a little bit about how Rust achieves its other promise, its memory safety without garbage collection. And Rust does this with the help of a novel system of ownership and borrowing. Well, it is novel in a sense that it is a first widely used language which has ownership and borrowing. The invention of this concept dates back a while years ago. So, what is ownership and borrowing? In Rust, you have values, and you have references to values. And reference is like a reference in C++ or a pointer in C. Not exactly like it, but pretty close. References can be mutable and immutable. Or, like some Rustaceans call them, they can be shared and unique. And what Rust checks at compile time is that every value has exactly one owner who is responsible to deallocating the value. It checks that if you get a reference to a value, the original value is alive, so that you don't have a problem like danger references and pointers. And finally, it checks this rather curious rule that you can't have 2 mutable references, or a mutable reference and a shared reference. If you have immutable references, it has to be unique, or Rust won't compile your code. That's like really hand-wavy. And really, my goal here is not to explain everything to you. My goal is like to spark your curiosity so that you can learn about this language a bit later. So let's start with ownership. Here we have an example function, which creates a vector of 4 variables. And this vector is like C++ vector or Java's array list or Python list. It's a buffer of 4 numbers allocated on the heap. Here, the owner of this vector is this XS local variable. So when the example function completes, when XS goes out of scope, it deterministically destroys the vector. On the closing curly brace happens the deallocating of the buffer in the heap. Local variables is only one kind of an owner. Another kind of an owner in Rust is structures. So here is an example of a trivial struct foo, which contains only a single field, XS, which is familiar to Rust vector. And there is a function which constructs this foo out of the vector. Keep in mind that this example is not exactly most simple and idiomatic Rust. I tried to make it like more familiar to people who are coming from Java. So yeah, also note that Rust separates, just like Go, the definition of the structures and their fields and the definitions of their methods. But if you forget about this, this looks like pretty trivial. We take a vector of integers and we create some structure out of it. What is fun here is that this new function actually takes ownership of this vector. So that means that in this example, when the foo structure goes out of scope, it frees the excess vector. At the same time, the variable excess no longer has ownership of this vector, so it doesn't free the vector, and it is freed only one time, so that's cool. And the side effect of this ownership transfer is that you actually physically can't use the excess variable after you pass it to foo : new function. Like literally, if you try to print excess, compiler will yell at you and say this is not allowed because there is no excess local variable anymore. The vector is moved into foo function. So that's kind of why Rust is different. And it would be pretty hard to program if any function call just destroyed all the arguments you passed in. For that reason, Rust has a concept of reference. Reference is spelled as ampersand. So here the function sum takes vector by the reference. And if you take a reference to a value, you don't actually claim the ownership of the value. So the value stays in place and you can use it afterwards. In this example, it would be totally OK to print excess afterwards or to compute sum 2 times or something like that. What would not be allowed in this example is mutating the vector, because this ampersand is just a constant or shared reference, which does not allow you mutation. If we want to mutate a vector, for example, we want to double every element, we will need a mutable reference, which is spelled as ampersand mut. In this example, we have a function which just doubles elements in the vector. And note how this mut is not like final in Java, in that it is transitive. We don't mutate the vector itself. We mutate only the values in the vector. But nevertheless, Rust requires that we provide immutable access to the whole vector to do this. So yeah, references. And what Rust enforces here is that if you have a reference to a value, that value must be alive. So for example, you can't create a local variable and return a reference to this local variable out of your function. That would be a compile time error, which is nice for memory safety. The interesting rule about this is that Rust forbids you from creating mutable and shared reference at the same time. Here we have a single local variable, x, and we create 2 references to it, one mutable and one immutable. And we try to add the variable to itself. And Rust yells at us and forbids this code because, well, there are 2 references, one of which is mutable, and this is verboten. And it's interesting because Rust is the language where the trick interview question, what does I+++++ I means, is impossible. Not only because Rust does not have this ++ operator, but because this construction, which tries to mutate and use the variable at the same time, is forbidden because of this shared for mutable rule. So this is pretty important to enforce memory safety, which I wouldn't go into too many details, but I will give a single example. Here we have our familiar vector. We take reference to the first element of this vector. So this x points to 1, which is stored on the heap. After that, we try to push a new element into the vector. And then we try to print the first element. The problem with this code is that if you add an element to a vector, it might actually run out of space in the heap. And in that case, the vector would need to reallocate the buffer, to allocate buffer twice as large, copy all the elements to the new buffer, and only then add the final element at the end of the new buffer. And if the vector does this, all the old values change their place in heap. So this original reference to the first element might be invalidated by this push operation on the 3rd line. And that's why Rust forbids this. More specifically, the reason why this is forbidden is that the push operation on the vector requires immutable access to a vector. So we have one constant reference, x, and when we try to call push, we are momentarily creating the mutable reference to a vector, and this is forbidden because this weird shared mutable rule. But as I promised, I wouldn't tell you about memory safety. I am going to tell you about concurrency. And this shared mutable rule sounds a lot like read-write log discipline. in that you can think of the reference like a read-write lock, and you can write to something only from a single thread, or you can read something from many threads. And it actually was discovered that this borrowing discipline really helps you to eliminate data races from your concurrent programs. Let's start with a simple example. Here we have our familiar vector, and we are still printing it, but we are trying to print it from another thread. So this syntax with pipe and curly braces is a Rust syntax for closures, which is inspired from Ruby. And note that we use a move keyword here. A move keyword here tells the compiler that we want to move ownership of this XS vector into the closure. That means that we will free the memory not when the example function ends, but when the closure in the other thread ends. And this is actually what you would like, because it would be bad to deallocate a vector before the other thread finished. Note that the side effect of using move here is that XS actually goes, sort of goes out of scope, and you can't use it anymore. And so this code is forbidden. And this code is actually an example of code which you could write in Java, and which would probably be buggy. In Java, you can create array list on one thread, and send it to another thread, and start printing this array on another thread, while at the same time, you are mutating this array list on the first thread. So on the one thread, you will be mutating, on another thread, you will be printing, and the result of this printing would actually, I think, be undefined, or you, for some collections, you might even get something like concurrent modification exceptions. So it's definitely a bug, and it's fun that Rust prevents it. If you look at this from a slightly higher level, this actually is an instance of message passing. And what Rust gives you is message passing, which does not require messages to be immutable, like, for example, in Erlang, and which does not deep copy the messages on message passing, like, for example, in JavaScript web workers. At the same time, Rust guarantees that from this dirty message passing, you won't actually get any concurrency problem, because if you send a message from sender to the sender completely loses access to the message and can't mutate it or any values inside of it anymore. So this is an example where Rust already is better than most high-level languages. Let's try something different. Here we have an array of 4 integers. This array is almost like vector, except that its size is fixed at compile time, and for this reason, it is allocated on the stack. And what we are doing here is we are trying to increment each value in this array. Note how this increment is independent for each variable. So we can theoretically speed up this code by spawning threads. Of course, it's stupid to spawn threads to increment only for variables, for elements, but if you imagine a much larger array, like 4 million elements, and some more complex operation, it actually might make sense to split this array and make each thread to process this disjoint chunk on vary. So this is just like a toy problem. One complication here, if we want to spawn threads, is that we can't use just std thread spawn, because now this array is allocated on the stack of the example function, so we somehow need to make sure that all the spawned threads which process this array actually die before we exit the example function. For this, we use a third-party library Crossbeam. This is a slightly tricky slide because you have 2 nested closures here, but bear with me. So this scope.spawn spawns a new thread, just like std thread spawn. But unlike std thread spawn, this thread is guaranteed to be joined by the time we exit the outer scope invocation. So this code actually works, and it does something really crazy. We are in parallel incrementing variables on the other thread stack, and Rust guarantees that this is actually safe. And the reason why Rust sees that this is safe is because when we iterate over the array, each time we get a unique mutable reference to a value. So the Rust compiler sees that these references actually disjoint, and it is safe to use them from several threads concurrently. If we try to break this code and introduce a data race manually, for example, by spawning 2 threads which try to implement the same variable, we actually get compile time error. So the fact that the code on the previous slide works is great. The fact that the code on this slide does not compile is absolutely amazing. This is exactly what protects you from shooting yourself in the foot when you write multi-threaded programs in Rust. If you try to accidentally share something which shouldn't be shared, compiler will just catch you and say that this won't do. Previous example was kind of easy because there was literally no sharing of data because all these references were known to be disjoint. Let's try to do something more complicated. Let's try to increment a single counter from multiple threads. That's a tricky problem for Rust. If we try to naively add crossbeam and threads, of course, Rust will catch us and say that this is not actually thread safe, because counter is a non-atomic variable. So if we are using it from several threads, we might get undefined result in the end, and Rust catches us. So what we need here is either to add atomics here or to add mutexes. I will show an example with a mutex because it is more representative of a real code. Like for integer variables in production code, you definitely will just use an atomic. But if this integer is a more complex collection, like some kind of a hash map or something like that, you definitely need a mutex here. And a mutex in Rust is a little bit magical in that it allows you to sort of not really violate this shared XOR mutable rule, but make it more flexible. Specifically, mutex allows you to transform a shared reference to a mutable or unique reference, proving that you actually have locked the mutex. And let's see how this API works in Rust. First of all, note that we literally wrap the mutex in the first line around our counter. So there is a saying that don't protect code with mutexes, protect the data. Here in Rust, this best practice is actually enforced by the API. You have to wrap mutex around your variable. Then this mutex would have a lock method. What this lock method does is that it, first of all, locks the lock, and then it returns a special guard object. And what this special guard object does is that it owns a mutable reference to the underlying data in the mutex, and it also unlocks the mutex when it dies. So note that there is no explicit unlock here. The same way there were no explicit free with the vector example. This unlock happens implicitly when guard goes out of scope. And we can extract from this guard a mutable reference. And then we can use it just like a mutable reference, like modify the counter in any way we want. And the cool thing here is that Rust compiler knows that this reference to a counter originated from this guard object. So the guard is the owner of this mutable reference. So Rust actually checks that as long as you have this reference alive, the guard object itself is also alive. And if you try to sneak this mutable reference outside of this closure to some global variable or a singleton, Rust again would just refuse to compile this code because it needs to prove that the reference does not outlive the guard object. So yeah, there are my simple examples. They are really simple and focus on arrays and integers. But I can't obviously show you this on the slide, but this really translates to large real-world programs. I definitely was saved from Rust when I've added a non-thread safe field to a structure, which was used in another structure, which was used in another structure, which was shared between 2 threads. And this ability to reason about thread safety of code through all the abstractions and layers of code is really liberating in that you can refactor Rust code safely and not really think about thread safety, because if you do something horrible, which will introduce a data race, compiler would catch you. Another question here is, isn't this like ownership and borrowing model too restrictive? Like shared executable rules definitely seems like something you need to contort your code to adhere to. And it's sort of true. Like similarly to functional languages, if you want to rewrite your program from like typical object-oriented language into Rust, you usually will have to slightly re-architect the program to make sure that all the values form a tree of ownership and you don't violate shared executable rule. At the same time, this restructuring actually works in large-scale programs. So people write large software in Rust, and while the architecture is slightly different from typical O program, it actually works. And yeah, in some sense, this shared executable can be thought of like the functional programming stands on immutability, that everything is immutable, but with the slightly increased flexibility in that you don't actually have to make everything immutable. You can mutate your data. You only have to make sure that only one thing mutates data at the same time. And yeah, that's, I think, it. I hope I've sparked your curiosity in the language. And if you have any more questions, please reach out to me or read the documentation, which is also awesome because of this man here. Thank you.
Hi. Thank you. So we're running a little bit early, so if anyone has we have time for a couple of questions in the room, so maybe just raise your hand and we'll give you the mic.
Can you tell us something about the comparison of Rust with C++ applications, any benchmarks or?
Yeah, so basically the performance of C++ and Rust exactly the same, provided that C++ code is actually safe. So it's like really easy to make C++ code go really fast, but horribly wrong. There are some cases where like Rust forces a little bit of an extra checks. For example, although most of the times array bounds checks are elided, especially if you're using iterators, sometimes you have to leave array bounds check in there. It usually does not affect performance, or if it like really affects performance and if you can really prove that no array out of bounds can happen in this bit of code, you can use unchecked indexing in Rust, which needs unsafe, which is a separate other talk, which I am not going to give right now. But yeah, in general, performance of C++ and Rust is on par.
Thank you for the presentation, but I have one question regarding the linking of Rust application to, for example, a C++ library.
Yeah.
And how does it affect the type safety, the safety of the Rust compiler?
So you can definitely link Rust code and any other code using the C ABI. The C ABI obviously does not have the concept of ownership and borrowing. And that's why using C APIs from Rust requires this same unsafe. Because like you as a programmer has to translate these rules of correct usage of C API, which are usually in the documentation, into the Rust type system, into like owned values, references, and mutable references. After that, you can use the wrapped C API safely. So the idea here is to take something unsafe and wrap a Rust type system over it and then use the safe wrapper. And in most of the cases, for most of the C libraries, such wrapping is actually possible. But there are cases where indeed like the C API does not map really cleanly to Rust ownership model, and that's kind of an open question how to work with these kinds of APIs. So it like works, but not in 100% of the time, but in majority of cases.
Thank you.
There's no second thought. I have a couple. I have just a couple of service announcements really quickly. You must all have a flyer with stickers to collect that you should have been given in your tote bag, and if you get all the stickers, all 9 stickers, you win a prize. Well, we gave you an impossible task because one of the stickers has not been printed. There's no sticker from. We wanted to be a realistic client experience. So Margaret Hamilton is missing. All the other stickers normally exist at last count. So don't get mad if you're just missing one. You might be winning. Margaret Hamilton. And if you don't know who Margaret Hamilton is, Google her. The next talk in English, if you're interested, will be at 10 past noon in the Saint-Exupéry room, which is the big one upstairs. It's about web GPU. And one last thing, as you know, we're running 10 minutes late, and because we're in France and in the Southwest, we absolutely don't want lunch to be impacted by that. So all the talks in the afternoon will be 10 minutes late as well, so you have the time to do that. If you still want to talk to Aleksey, he'll be at office hours in the ground floor about, I guess, 10 minutes from now.
If you have more questions, I will be downstairs.
Great, and let's thank him once more.